Good morning. Welcome back. Today will be lecture 7. Up to lecture 4, we understand how to create a seismic stack section. And then weeks 5 and 6, we try to learn how to create the high quality stack section, right, by removing random noise and coherent noise by different filtering. Today, we're talking about how to generate geological profile. Seismic stack section is not really geological in terms of a structure. So the title is called a post-stack migration. So we need a good stack section, and then we do the migration based on the stack section. So stack section means every trace in the stack section is equivalent to zero offset acquisition. So source receiver are in the same location. So the whole processing, like NMO processing typically, is for this purposes too. So now we assume we already have a very good stack section, and today we just focus on that. Today we're talking about post-stack migration. I divided this lecture into 3 parts. Right. First of all, it's a modeling and the migration. Try to give you some intrinsic concept explanation. So why do we need a migration, and how we achieve migration? How do we implement migration? And then we talking about 2 groups of methods. One's called Kirchhoff migration or diffraction stack. We will see the difference. This first group of migration is integration. According to the name stack, stack means summation. Summation is a discrete form of integration. So the first group of methods is integral method. And the second group of method is a equation-based method. Modeling migration. In the previous lectures, we learned how to generate zero offset stack section. So zero offset means, I denote M here. M here just denotes the midpoint, right? So source receiver now, source receiver distance, source receiver offset is 0 because of an MO. So that's the midpoint. That means the source receiver same position, so you have a wave propagating from source down to the subsurface, reach to the reflector, and then come back, right? Because it's a 0 offset, so based on the minimal travel time principle, your wave travel always go to the fastest way. So minimum travel time. That means this ray path always perpendicular to the targeted reflector. So this 90 degree here, perpendicular, okay? Now, assume we have a deep reflector here. So from this point, you receive a signal from here, right? Come, move propagating down, and come back. So this is a reflection. That's in a model space, right? Geological model. But in your seismic data, in your seismic trace, in the data space doesn't, you do not, the data does not know this sample, where's the sample from. They only put this one on the just below this CMP point, right? So now this dashed line here actually is a seismic trace. You record at this position, or after removal at this position, right? You do have a sample here, but you do not know is this one, or where is this from? It's from here or from here, right? So that's why we need to do migration. Migration means you move the sample data points into the right position, so-called migration. You should move your data sample to the right position, okay? So one thing here I emphasize, you should distinguish in model space and the data space. In this context, you should distinguish into reflectors, and the reflections, okay? Reflectors are model space, geological model, the true physical model, right? But the reflections are the data samples that's in the data space. So migration really means you try to, based on your data space imaging, create a model space image, which means geological image, okay? That's the whole purpose here. The ultimate purpose is to try to image the subsurface structure of the Earth. So how do we identify the different structures from your data space, right? Before we do migration. So you should know what the geological structure looks like in your data space before you do migration, right? So that's why I put my modeling and the migration in the same section here, right? So let's see some subsurface structures. Here, this is a deep reflector, okay? Very short. And in your stack section, for example, if a source here, you receive something from here, but you put it underneath of this midpoint, so it will be here, right? Or another one, source here, receive here, because it's always perpendicular. This will be put underneath this. So in your seismic stack section, this dipping events will be shallower. It's not that deep. It will be a more sort of gentle dip, right? Rather, that's deep and deep, okay? That's one thing. Secondly, this length of this line segment in your stack section actually appears longer, right? We can understand this because this one, if the point perpendicular to this, that point here, if you will try to find the point perpendicular to this one, will be here. So because of the angle, right, you can see this distance longer than the actual length of a structure. That's why in your stack section, your refraction looks longer than the true length of a reflector. Okay, that's the one structure. For this type of structure, it's called syncline in the geological term. Syncline, for any of this point, as I said, we always find that the ray path perpendicular to any point, right? So now, for example, if we have a middle point here, in the middle, you can have one perpendicular to this point, bottom one perpendicular to this point, left-hand side also perpendicular to this one, right? So in some places, you have 1, 2, 3 possible perpendicular rays, right? So at the end, this syncline structure, syncline reflector, becomes, looks like a bow tie in your stack section, right? A bow tie stack section, okay? Very nice bow tie. So when you see this, you can immediately interpret your seismic profile and say this must be a bow tie, right? However, if this bow tie, if this syncline, all right, if this syncline is much wider, basically just a straight line but slightly bended, right? Up in your data space in the stack section, that's also syncline. This is also syncline but narrower, right? So if too narrow of a syncline becomes a bow tie, but as wide syncline becomes a narrower syncline. You can easily use a forward modeling tools to generate the seismic image for zero offset. For anticline, you can understand for the left-hand side, this point, the midpoint must be far left, right? For the right-hand side, this corner, the midpoint will be far right. So you can see the first point to the last point distance quite larger than actually the aperture of this anticlines, right? So this is why in your stack section, this anticline appears much broader, much wider. Okay, so just I emphasize that this one, the top, this one is on the trace at this midpoint. Okay, midpoint. So that midpoint, this one to this one, distance between these two midpoints, one's perpendicular to left-hand side point, one's perpendicular to the right wing of this anticline. The distance between the two midpoints are much wider. This is why your stack section shows much wider anticline structure. Okay, so this one should be easy to separate from this bow tie, because bow ties not only have this syncline here, but also have other two wings here. Okay, that's the anticline. If the width, if the aperture of this anticline becomes extremely smaller, right, to one point, right, that's single point. That becomes, we call it diffraction. Becomes a diffraction in your stack section. Okay, diffraction. It's just, you can see, because it's a single point, almost every point on the surface can have a perpendicular ray path. Go to this point and come back, go to this point and come back, propagating down to this point and come back, propagating down to this point, all right? Because this is a surface, we call it refraction seismic. Refraction seismic, your source receiver points on the surface. Otherwise, the scatter in the model space, we call it scatter or scatter point, right? You can almost have a 360 degree, we call it diffractions, right? But only because your source receives on the surface, you have this sort of a diffraction only half of that, or even less than half, okay? Maybe 45 degree for each corner. So this is the forward modeling. And what we try to do for migration is we try to convert any of this sort of features from your seismic stack section to those structures in your image, right? So generate the geological meaningful profile. That's the migration process, okay? So the name of migration came from this point move to here, this point move to here. This is called migration. We'll see more in detail. Right, let's see stack section. Right, you can see here, this just like a bow tie, right? You can see there? That's response of syncline, narrow syncline. Okay. Here could be this maybe not a simple syncline. Maybe this is just a diffraction. It's a diffraction. Okay. So, but if we learn the geological course, none of the structure represents any meaningful geological structure, right? It's hardly to see anything in the subsurface look like this. However, for this flat layer, because your ray path perpendicular to the refractor, so refraction actually is in the same position as the refractor. So for the flat layer, you do not, migration percent will not change anything, right? So how to solve this problem? How to make your non-geological seismic profile into the geological image? The solution is migration, right? Because we have already done the stacking, so the seismic profile is a mimic a zero offset image, right? So what we talk about today here is actually it's called zero offset migration, right? The purpose is converting the refractions into refractors. That's as simple as that. So why is it called a migration? Migration means we reposition the refractions to the actual geological point, refractor point. That's called migration. So data in your profile is just a shift around. That's called a migration. So the purpose of migration is this: if we have a stack section, again, stack section is in the data space, right? In data space, you try to this interface your point A, source receive point at A. Actually, you have a data underneath here, right? This is your seismic section, but in fact, at this point, this one actually came from here. Your ray path perpendicular to the refractor. See that? But in your seismic stack section, you only see because your midpoint at A. So this point actually is stored in the seismic trace. So what we try to do, we try to put this back to the true position. So actually put the A to the true position. The true position of a migratory point is horizontally at CMPB. Vertically also shift up a little bit, right? So always upward shifting along the dipping events. You can see from here, move upwards, right? So new position is from A to B now. New position is B, not A. And vertically, this also move up. Okay, we were talking about how to, the distance A and the B, between A and the B, and the time shift between this point and this point. All right, so this we call the delta X, this we call delta T. This formulas are simply called migrator's equation, right? It's very straightforward, simple forward, okay? So what migration is for, I just repeat. For migration processing, you try to convert this dipping reflection into a refractor, which is much shorter in terms of length, but in terms of dipping angle, it's much deeper, right? Okay, And that this one always move upwards, okay? Move up dip, and also shallower. So short, shallower, and upper dip. That's for the straight refractor. For bow tie, in the stack section, in your zero offset section, bow tie, after migration becomes a nice syncline. For a broader bow tie syncline, for a narrower for narrower syncline, after migration becomes also syncline, but much wider, much broader. For any anticline, appears appeared in your stack section, after migration becomes a narrower anticline structure. So this left column is in the data space, right column is in the model space. You always, because you are geophysicists, right? You always think about different domain, different space, data space, model space, right? So first thing, when you analyze anything, you should, first of all, you should define this in the data space or this in the model space, okay? For this perfect diffraction, we'll see perfect means we'll just follow some equations, right? And later, for this perfect diffraction, that's after migration will become a dot. This one is very important because one of the migration methods, you assume anything in your seismic profile is diffraction. You just sum them together, follow this diffraction curve, and you image all points. But if the summation is 0, means there's no diffractor. If summation non-zero, you have some amplitude appear, right? So that's the one of the principles for migration. We're talking about this in detail later. Right, now, we saw this stack section. There are some data structure which are not geological meaningful. For example, the bow ties, diffractions, right? Or maybe this dipping events. You know, after migration, what it looks like. It should look like this. Let's do the comparison. You can see here, this is a syncline, right? For this small syncline, in your seismic data, it appears as a bow tie. Let's see. Bow tie here, okay? Yeah. Here is end of a structure. Maybe this is some discontinuity here. So this one, the terminal point of a structure, which is like a scatter, right? So that means in your seismic profile you should find a diffraction, right? So let's see. Point here. You can see the diffraction here, right? But you maybe left-hand side, you do not see much because this may be hiding somewhere. Cancellation of other diffractions. Right. For this dipping event, actually, this migration section, you can see this dipping event here, but in your stack section, the dip event should be longer, shallower, and a gentle dip, right? See here, that's a gentle dip, but much deeper. It's the general observation. You can do the comparison between the two, right? So this looks like geologically meaningful. Well, not necessarily always true, right? But you do have something here. Maybe this is the artifacts that we're processing, right? also you say, okay, what type of geological structure look like this? That means your migration image need further improve the quality, improve the so-called focusing, right? Just like you do a camera, you need to tune in the focus, right? So that's the improvement, the room for the improvement, okay? But in general structure, this more looks like a subsurface structure rather than the diffractions or refractions in the seismic stack section. Let's see detail here. This is another example, right? This is a typical bow tie. You can see that. I just enlarge one for examples. There's another bow tie. You can see. Maybe there's another one, small one. But this is simply a diffraction. Well, this is a simple diffraction. This is another diffraction. So this diffraction and the cross of this diffraction. Well, in the subsurface, you do not see hardly see any geological feature crossing each other, right? If I fault, it's just completely separate two parts structure. You do not see the fault, the crossing features. So this is a stack section. So after migration, they should be migrated to the right position. This one highlights these four parts. You can see the difference. That's a syncline. This is the largest syncline. This is a small syncline. You see that? Okay. So that's syncline. I said there's another syncline. There's a bigger syncline. You can see this one, right? But here, you do see some, there should be some diffractors. Maybe this is over migrate. Over one migrate means usually have a like a syncline structure. Sorry, anticline structure. I mean, structure in your data, right? Not a subsurface structure. After migration, you do see something like a syncline curve here. That syncline, I'm borrowed terminology from a model space, right? But actually, just this not really subsurface structure. So this seems like an over migrated. Ideally, it should be single point or flat line. Okay, this for the deeper part. Right, that's the bigger image of this profile. That's the stack section. You can see some of diffractions or bow ties here. Very detailed structure. And this one, this deep events, overlaid by this curved refraction. After migration, let's see three parts, okay? This bit, maybe this bit as well. And then this structure. Let's see what it looks like. You can see now. So all the diffractions disappear. You get this small, because of scale now, right? This syncline is focused, or maybe some diffractors appear. Those diffractors could be sort of a fracture zone here. You can see that each fracture point becomes a diffractor. So you have quite a complicated diffraction here, but after migration, you can see, okay, you have continuous interface, but here between there's some like a fracture zone, right? Like a volcano came out. Yeah, and for this bit, you can see much clearer fault here. You can see that. Okay, much clearer faults. But so this profile is easy for geological, much easier for geological interpretation. And for these structures, if you remember, those are the linear refractions after migration, deeper. The scale, you do not see much difference, but they always move upwards, okay? For those structures, because they are in the horizontal form, migration hardly move them, right, in the large scale. Let's see this one before migration, after migration, see what it looks like. So here it's much clearer. Why? Because there's lots of diffractions behind. After migration, all the diffraction collapse into a single point. So this becomes much clearer. Let's see here, see that? Okay. So that's migration also makes the resolution much better before the compared to the stack section, right? Let me just emphasize this. You can see here you have lots of so-called diffractions. Here diffractions, basically it's a scattered diffraction caused by scatters. Right after migration, all the diffraction collapse into point, and then this linear events become much clearer. Okay, that's the migration. So migration is very useful technology for seismic imaging, and the migration result is useful for the geological interpretation. So let's sum up the observations so far. Right, for the horizontal reflections in your stack section, migration will do nothing, right? Because for any horizontal reflection, your midpoint actually is exactly on the top, right? Which is 90 degrees perpendicular to the reflector. So that means the distance between two midpoints will be constant after migration. You see that? That's why for horizontal reflections, after migration, you do not see any change. Maybe you have some changes due to the small angle or due to the artifacts, but it should not. And for the dipping reflections in your seismic stack section, after migration, they become dipping, right? So the angle of a dipping angle is larger than the dipping angle of reflections. Okay, and generally for the dipping reflections after migration, the reflector size is shorter than the reflections. I already explained that because of the angle. So the surface CMP distance actually longer than the actual size of a reflector. Right, and for all dipping events, the reflections always move up dip. That's always, right? No any excuse, always move up dip. So in general, migration is for converting reflections into reflector, converting your data into a model. That's straightforward, okay? Converting data into the model. So you should know this data space or model space. Right. We have those observations, but now we try to do some quantitatively. See, okay, we said the dipping angle becomes larger than the dipping angle in your stack section, and the distance, the length of reflections becomes shorter in your migration section. So let's do some quantitative analysis now. Again, we should start with the definition of data space and the model space, right? So this in depth depth means that's x, the depth. Depth is geological depth. So that's in the model space, right? This model. In the model space, if we have a reflector, which is length from C to D, the CMP point, S and G, S means source, G is geophone, they are at same position, so CMP A. The A point is have a ray path perpendicular to the reflector at point C. That's 90 degrees, yeah? And for the another point B here, this ray path perpendicular to the reflector at point D. Because of the angle, the distance between A and B is larger than the length of a C and the D, right? That's easy to understand, okay? Because of the angle here. So this angle, theta with a bar on the top, that's I call it just sine theta. You can define sine theta equal to this, right? That's the delta x. This is the delta x, and here, sorry, this one from A to C. Here is a velocity times delta t, because the ray path is twice, right? From A go to interface and come back. So that's the total length, travel length, but actually the depth is halved. It's halved because delta t is doubled. Okay, so you can see the sine theta equal to delta x. This is delta x, right? This angle equal to this angle, right? I have a red dashed line here. This theta bar, we can have a theta bar here. Theta bar, if we define a sine theta bar, is opposite length, is this one, from here to here. That's a half of the V delta t. Delta t means that from here to here, and then from here to here, the same travel time, right? Delta t means the B travel longer than A. So that's the delta t. So where we travel down, come back. So the delta t actually double the time. So delta t time velocity is double travel distance. So for this triangle, triangle, you should have half in terms of length, right? So that's the sine. Sine theta bar equal to this length over this length. It's easy to understand, okay? So this analysis is in the model space. In your seismic profile, which is in the data space. Data space, horizontally, we still call it X, but vertically, instead of Z, which is depth, but now your seismic trace, single trace here, actually vertical axis is time t. So you can see the data space, time space, or model space, sorry, depth space, time space, or model space, data space, okay, different. So in your seismic data, in your seismic profile, you do not have a theta over bar, you have just theta. That's the reflection, this is the reflector, right, this refraction. The reflection, all right, A and B, that's on your seismic profile, so these 2 points are fixed, A and B. So that's delta x, same as this one. But the delta t now, let's see. From A to C prime equal to B to this point, right? So delta t prime, delta t will be from this point down to here. Okay, so this angle equal to this angle. This is delta x. So this delta t, if we convert into the meter, there will be half v delta t, right? Delta t same as here. This delta t over delta x becomes a tangent theta. Right now, you can see the right-hand side is the same. The ratio of this distance over this, here, this distance over this, the right-hand side, the fractions in the right-hand side are the same. But the left-hand side, in the geological space, in the model space, this fraction is sine theta bar. But in your data space, in your seismic profile, this ratio defines a tangent theta, right? Okay, so this tells us what people, when I was a student, my lecturer actually made a joke, right? If we want to be a geologist, if we want to be a geologist, you understand how to define sine theta is good enough. But for geophysicists, you are much smarter because you understand the ratio of sine theta to cosine theta. Right? That's a joke, okay? So it means in the geological space, everything much straightforward, simpler. But in the geophysical space, in the geophysical domain, everything becomes more complicated. Right? Even for this simple example. So what the geophysicists try to do is to try to simplify everything. So as I, conclude my life in the geophysics field, we will actually do two things. A, we try to detect anomalies the whole life, just like a doctor, medicine doctor, right? You have a patient that went to the CT room. When he got the image, right, what he tried to do, a doctor, or she tried to do? She always tried to identify some anomalies. Just look what we do here, right? The second thing, if we are good geophysicists, you try to simplify everything so that people can understand you. So in this case, in migration, we try to simplify your seismic profile to generate some images simpler but meaningful. Okay, so two words: anomalies keyword is a keyword, and simplification is our duty. Okay, so this helps you to remember these two equations. Okay, one is the delta t over delta x. This is the ratio. But in geological sense, this becomes sine theta over bar. And in the geophysical sense, this becomes tangent theta. So in the data space, this is tangent theta. In the model space, the sine theta bar. So you can easy to memorize this equation. Just what I promised from very beginning of the lecture. We do not try to force you to memorize the many equations, but through this simple logical understanding, you can write down your own equations. Right, just two equations, you can write down own equations. Right, this is my expectation from this lecture. So to the left-hand side, there's the modeling. To the right-hand side, there's data. So if from this is a data space, is model space. So modeling means you, based on this model, generate seismic profile. Migration means you have this data profile. You try to reconstruct the subsurface image. That's the migration. Okay, so the migrate equation, we have so many equations, but or at least we have two now. But you should remember this equation. Geological angle, sine theta bar, equal to tangent theta, equal to the angle tangent of a geophysical angle. That's the simple equation. Now, because we define the theta or theta bar in terms of a ratio of delta t over delta x, now we just try to do next step. How to quantitatively estimate delta t, estimate delta x. Okay. Remember this formula. We said sine theta bar equal to half of the v delta t over delta x, right? So just delta t delta x. Remember delta t delta x in the previous lecture, we call this a dipping angle, right? How many milliseconds per trace or something, right? Dipping angle when we're talking about FK transform. You see that? So actually this is also used for in the future called FK migration, also based on this. So delta t is from here to here, that's delta t. So basically this is a seismic trace. After migration, this point should shift to here, migrate to here. So this is a delta t, and here is delta x, okay? Horizontal shifting, that's called delta x. Vertical, always move up, that's the delta t. So delta x, based on this formula, you just reformulate this, you end up that's formula. Easy, straightforward. Okay. And for delta t, your delta t started complicated because delta t is this one. It's the total t minus this t minus this dashed line. So total length for t minus this one. Total length, this length equal to this length, right? Because this point are perpendicular to subsurface refractor, but this one should the length of this should equal to this. Okay, so basically the delta t equal to this red length, the length of the red line minus the dashed line here. So 1 minus dashed line, which is cosine theta over bar, right? Cosine theta over bar. Okay. Mathematically, you know that in high school, cosine theta equal to 1 minus sine theta squared. Because you know the sine theta here, so you just replace the sine theta here. You end up with this formula, right? It looks like complicated, but actually it's straightforward, you know. Delta t equal to t minus this segment. X is this one, delta t is this one. T is this one, so you just minus. Right, this is the two formulas, okay? We do not do repeat this equation here, but we can use the equation to get some straightforward idea, you know, what the migration looks like. Let's see. In your, I have two sections here. One's this dipping event, another one that one. This dipping angle larger than this one. That's called theta t in that space. That's called theta t over bar in the migration section. Okay. And based on this, you can know this in the data space. The CMP point is here. After migration, this point moved to here, right? So just same as the previous diagram. The difference in terms of time, that's called delta t. The distance over here, it's called dx, right? So that was the formula summarized here. But now, that's in the data space. What I try to tell you now, the delta t delta x is in the data space, but in the model space, delta t over delta x, how you compare this? You basically just try to give you the distance of x, distance of t here. This slide try to give you the difference between the dipping in the seismic profile and the dipping angle in the migration profile. Okay. So based on these two formulas, you can easily derive this. Now, let's see example. I just repeated the three equations. One is the dx, one is the dt, one is the dipping angle in your migration section, represented in terms of a dipping angle in your stack section, right? Of course, depends on velocity, because your travel time does not have same unit as a horizontal distance. You must have a velocity, right? You transfer your time into the distance. So the velocity. In this example here, quantitative demonstration, we assume velocity is constant. Most likely, that's not true, but for just like an MO, we assume constant velocity for some specified location. Okay, now, if we use seismic data, seismic trace at 1 second, it's not zero, right? At 1 second. If the velocity from a surface down to the 1 second is 2,500 meter per second, so the dx here, okay, let's see. In your seismic profile, you have a dipping event, which is a 10 millisecond per trace. Okay, the trace interval is 25 meter. So have a delta t delta x equal to 10 over 25. Right, that's your delta x. Okay. So dx here, based on this formula, you have a dt dx. You also have v. You also have t. T is 1. V is 2,500. So this one give you delta x. Dx give you dt. This is in your seismic profile. You know this one will shift, horizontally shift quite long, or 625 meters, quite a long distance, right? And the vertically also shift quite long, more than 100 milliseconds, 134. Right? The dipping angle in your seismic data was 10 meters per second, per trace. But after calculation, you can see now it's 11.5. It's a deep, slightly deeper, right? Now, for 2 seconds, your velocity increased a little bit. It was 25, but now 30, 3 kilometer per second. The dx shift even large, very large, 1,800 meter. So you cannot simply ignore it, right? Huge. And the dx also huge. It's already 400 milliseconds, quite a lot. And the new dipping angle from a 10 degree, let's say, well, just call degree, right? The dip from 10 to 12.5, already 25% deeper. You can see there's even larger effect. Now it's a 14 degree, just was 10, now it's 14, right? This sort of a numerical calculation gives you a sort of quantitative idea why the migration is so important, because any of this cannot be ignored, right? The horizontal shifting, this shifting 3,675 meters, 3,675 meters. It's quite laterally shift quite long. This one vertically only for 3 seconds, but now it's almost a quarter, right? Oh, actually more than that. See, it's 800 milliseconds. Vertically shift quite a lot. Horizontally shift huge. They have a huge movement. Vertically move up quite a lot. And the angle now from 10 now becomes 14. It's 40% different, right? So this is very important. Then the times are longer, deeper. This dipping angle becomes large. You can see the effects, right? So that means we cannot, in any circumstance, you cannot assume your stack section is immediate section, right? You can see it from this quantitative estimation here, right? So let's just show you one example. That's obviously, because this angle larger than this one, the length of this event shorter than this one, obviously this model, right? That's data. Okay, don't just simply think because I write a model here, write a data, just simply see these two words here. Maybe I mistakenly put in the wrong position, but based on the observation, you can see this angle is larger than this angle, dp angle, and the length, this one shorter than this one. So this is in the model space, this in the data space, right? Okay. So for examples here, we have a 45 degree, 40 degree, 35, reduced by 5 degrees until to 0. 0 is horizontal, right? So after in your stack section, you have the length the same, but at the end here, you have a half of a diffraction because another half cancel the we'll see detail, right? Okay. So this simply tells you migration is a really, really important step for geological impression. You cannot simply assume in any circumstance, you cannot simply ignore this effect, right? You cannot use stack section to do the geological implication.